Hello, this is page 231 and this is class 25 on March 25th, Wednesday. So this is where we're going to start. It's kind of the activity part 3, but I blocked most of the things, so we are skipping so much. Just want you to read the step 21.1. So looking at the diagram here, we are going to examine the work done by the applied force changes, but again we are skipping most of it. So what I want you to understand here is in this experiment, a spring will be connected to a cart, and as the cart is moved, we will record the position of the cart and the force exerted by spring. Okay, so this is kind of what we are doing. There's a spring in the cart, and there's a stretch and compress, and so we are going to examine the work done. So those are the pages that you're skipping. Next thing you do is 2113. That is the couple, there are 4 of them, clicker questions. So using that picture and the kind of the statement, so we're gonna answer those questions on Canvas. Okay, these are the clicker questions. Not all of them are related to that, but the first 2 questions you can kind of visualize the problem looking at the statement earlier. And after that, again, this is the summary of the part. So the K was capital, I made it smaller, but these are really important, as I mentioned before, so please focus on these. Okay, so I'm going to put a star here. The force created by a spring is in the form of spring constant K, and the compress or stretch, the displacement basically is X. Okay, so K times X, that is the magnitude. We can get the spring constant K by finding the slope on a plot of spring force versus spring stretch, so F versus X, because it's a linear relationship. And we can compute the work done by a spring or any other force as the area under the curve on a force versus position graph. So those are the recent clicker questions that hopefully you've worked on. And when we use conservation of energy and compute the work done by the forces, we need to look at each force separately. I'm gonna put check marks. We use different methods depending on whether the force is constant or changing. Again, there are a couple examples we've done so far, at least 3 I believe. So we are learning the methodology behind this, and that is going to be very important. So again, this is the step that is very important for the next chapter as well. And last time I also showed you, and there is one example that I showed as well. This is the work done by the spring force. There's so many typos. And this is the form, and you'll sometimes see it as WS, sometimes WF sub S, but we usually try to put a subscript so that we can kind of show that it is a spring force. Okay, so that is the work. Okay, so we looked at these several work done, constant force, variable force, some specific variable forces like spring force. And hopefully we learn how to figure out the force term, the work term in the energy conservation. Next subject is about power. This is the last part of chapter 7. We will be using this later as well, but first let's define what power is. Okay, so here's an example. Gonna highlight what I'm talking about. So example is homework. The goal is to get it done correctly, right, and quickly. So you don't want to spend 6 months on one homework. That means you're not very powerful. So if you do it correctly and quickly, that kind of shows you're very powerful. You have really all the knowledge and such. So power is defined as the rate. So this is really important. Rate at which work is done by a force. Okay, so that's the reason it is defined as work divided by time, the time interval. Okay, so often we care about how fast the work gets done rather than the amount of work, and that is the measurement of this is power. Okay, so that kind of tells you how powerful it is. So average power, as usually has been, we've done it before as well. For average, we use a bar, right? So that's why we have P bar. Capital P is for power, and that's what we are using here. Bar shows it's the average, and to find that, it is simply the total work done divided by the time it takes. Okay, so delta T is a finite time, some time interval. Instantaneous one has no bar on it because it's not the average, right? Just like before, again, we used it for different things. The only thing is power, as you kind of see that since it is the rate at which work is done by a force, and work is not a vector, time is not a vector, so you shouldn't think that power is a vector. And power is scalar, okay? But can have average or instantaneous values. So for the instantaneous one, as usual, we take the limit and we get the derivative of the work done over the time again. So it's for a given amount of work done. Low power means it took a long time. High power means it was done very quickly. So what are the units? In SI units, we use watts, and that is defined by joules per second.